What you're listening to now is an experiment. This podcast is available in 2 languages. The following podcast is an English version of the German edition. It was translated and voiced with the help of artificial intelligence. The original can be found at mancherorts.de and wherever podcasts are available. Many thanks to Phillip Scheffel for participating in this experiment.
Mancherorts, es fliegt. Ein Podcast von Rainer Suko. Hören Sie Mancherorts. Überall, wo es Podcast gibt. Und bei Radio SKW.
Mancherorts is a podcast by Radio SKW and podcaster Rainer Suko. Whether an individual, association or project, Mancherorts gives your story a voice. We tell your story.
We are about to see a very impressive airplane, which actually looks almost exactly like what we've been seeing on screens for years. For the first time, it will properly see the light of day coming out from the dark hall into the sunlight. How we bring the plane out will be a surprise.
For the 3rd time, I am visiting Strausberg with Mancherorts and accompany the company Apus on their journey to build the world's first commercially hydrogen-powered aircraft. In early August 2024, I meet Phillip Scheffel, the CEO of Apus. I started by asking him how far along they are in developing the first prototype of the Apus i-2, which will taxi and fly.
Well, we're in the final sprint on the way to the first flight and on the last stretch towards the rollout. The aircraft is nearly complete. All the parts are in place with only a few missing. The rollout event is scheduled for September 6th. After that, the aircraft will be fully assembled and ready for ground and system tests.
And we'll be heading over there later, but first let's talk about a few things. Last time we discussed the Ironbird and various testing procedures. Now that we've passed that milestone, what has happened in the last 2, 3, 4 months?
In the last 2, 3 or 4 months, all the components that had been built separately for a long time were finally brought together. The sub-assemblies started to merge, which you can imagine like droplets coming together. At first, there are many small individual parts. Then the first small sub-assemblies are formed and they keep getting bigger. Finally, the 2 large components, the wings and fuselage, were joined, and now it looks like a complete airplane. The landing gear, which we designed ourselves, was installed. The nacelle, where the electric motors and batteries are housed, was bolted and installed, and piece by piece the entire airplane came together. What amazed me was how smoothly everything fit together. Suddenly, nearly all team members had to work on the same task in sync with the schedule, and it went incredibly well.
Was there anything during the merging of these parts where you thought, oh, we didn't expect that? Or any challenges?
Not really. We had thought ahead to many of the risks and minimized them, so there weren't any major surprises. Our last major issues occurred back in February when a few things didn't work out, but we still had time to resolve them. Now 90% of the tasks are completed, and while surprises can still come up during the testing of the propulsion system after the rollout, most of it has already been pre-tested. So we're not expecting too many issues. The last phase went without major problems, and we've stuck to the timeline completely. Sure, some tasks took a little longer than expected, but the team has managed it well and will meet the planned rollout date on time.
I am sure it will be a fantastic day. As I prepared for today's episode, 2 things kept coming to mind, both of which are crucial in some way. First, there's the hydrogen propulsion, the unique aspect of using hydrogen to power the engine. What makes it especially challenging to have a hydrogen source in the air rather than on the road, rail or water?
Well, the key issue is that you can't pull over to the side if something goes wrong. This very complex system, fuel cells, converters, hydrogen lines, pressure regulators and so on, has to work perfectly from the start. Nothing can break. In lower altitudes, the atmospheric conditions don't pose any big challenges like thinner or colder air. In fact, in some ways, it's easier like having a constant airflow, unlike in cars that stop and risk overheating. The plane is always moving, getting fresh air. So some things are easier, but the main issue is the system's reliability and secondly, the weight. in a car, you can afford extra weight, especially in early stages, by over-engineering certain parts for safety. But we can't build in too many safety buffers in the i-2, otherwise it would be too heavy.
My second question is about the wing test images I saw. The large, heavy hydrogen tanks are located in the wings. Wings are dynamic structures, so how do the tanks fit into that?
We have two approaches for this, and we're developing both in parallel. One involves the tank being structurally decoupled from the wing. It's smaller than the wing and can move independently as their deformation behaviors are different. The tank expands lengthwise while the wing bends, and they mustn't collide. The other, much more innovative concept is to integrate the tanks into the wing itself, so the wing deforms along with the tank during fueling. The tanks must also follow the wing's deformations. This approach is more promising for the long term, but also more difficult to implement.
But there is a way.
Yes, there's a way. This prototype uses the smaller decoupled tanks, but the integrated wing concept has already been built and tested and will continue being developed in research.
So, as the energy source, we have the hydrogen. The components that convert hydrogen into electricity and drive the motor are basically ready and tested?
Pretty much, yes. There are still some failure scenarios that haven't been tested, but those will be addressed now. The interaction between the redundant propulsion systems and the electromagnetic compatibility still needs testing, but otherwise it's mostly done.
Apus aims to build the first fully certified hydrogen-powered aircraft. How realistic is it that this first commercial product will come from Strasbourg?
Yeah, it's realistic. The big challenges now are securing follow-up funding, reducing weight, and finding industry partners. But this aircraft proves the feasibility, and the fundamental architecture will be viable and certifiable.
I recently heard about a small company that failed to scale to mass production. How far is Apus from serial production? And are there any hurdles?
In aviation, it's never going to be like the car industry, where thousands of units are produced. We're talking about a few hundred. So the production process is closer to prototype building. If you've built a prototype, you've already tackled much of the production process. Of course, tools and fixtures will need improvement, but we're on a good path. And around 60% of the necessary tools are already in place.
Tools are a big issue since you need them to build a product.
Exactly. This is all carbon fiber composite construction, so we need molds for every part. They've all been made and are available now. While they might not be robust enough to last through an entire series, we'll replace them gradually. But as I said, we're on the right track.
On the way here, I saw many wind turbines, some stationary and others turning. Today is a sunny day, so it seems there's plenty of solar energy around. This brings us to the topic of energy, hydrogen, and its availability. Last time, we discussed that it's a major challenge. Are there any updates in this area?
Well, the development is ongoing. Hydrogen production capacities are expanding. Electrolyzer technology is improving and production capacities are increasing. The hydrogen market is developing, but we're still a bit early for it, to be honest. This is one of the challenges when introducing the product to the market. We can't be too late in comparison to our competitors, but we also can't be too early as the market might not be ready yet. Apus has the advantage of also being an engineering service provider, so we can balance things out by continuing that business.
There's been a lot of talk about a hydrogen backbone for Germany. Does Apus benefit from these initiatives, or could you do without them?
Since we actually need hydrogen, every molecule produced is a step in the right direction. We will definitely benefit from these efforts because a hydrogen infrastructure for transport, whether through pipelines or trucks, will be necessary. Hydrogen filling stations will become available, and access to hydrogen as well as its price will improve over time.
And it will make it more realistic to power things like airplanes. So let's build some anticipation for the listeners. What are we about to see?
We're about to see a very impressive airplane which looks almost exactly like what we've been seeing on screens for years. You'll see many people working on it, pulling cables, installing coverings and making adjustments. And I'll describe the rest when we're there.
Okay, then there's the rollout day. Does the plane drive out under its own power, Or how does a rollout work?
No, it won't drive out under its own power. For the first time, it will properly see the light of day coming out from the dark hall into the sunlight. How we bring the plane out will be a surprise.
Okay, well, let's head down there then. We are now entering a large hall. What is the name of this hall?
The final assembly and testing hall, which we opened last year and is now fully occupied and in use. The first part of the hall we are entering is where other aviation projects are handled as part of our engineering services. You'll also see the Apus i-2 here, a project we're working on with Rolls-Royce, as well as in collaboration with Cottbus and other partners.
That already looks like an airplane.
Yes, all the parts are here, the final assembly is ongoing, and once the i-2 assembly is complete, we'll move into the home stretch for this project too. The plane should fly next year as well.
Does it also fly electrically?
No, it's a different concept. It's essentially a flying test platform for testing electric propulsion systems, but it has 2 certified engines on board. This allows us to test at lower safety levels.
And here we see the Iron Bird. The bird is plucked.
Exactly. This is the first Iron Bird, which you know well. We've reused some components in the second Iron Bird, recycling parts like the coolers, which didn't need to be newly acquired. The old fuel cell is still there and it would technically still work. This hall is where all clean work is done and cleanliness is required, such as for avionics and electronics. There are 15 engineering workstations here where the avionics panels are developed, the wiring harness is built, software is developed, and high-performance electrical components are integrated.
Now we're probably going to go through a door and...
We'll see the current jewel of Apus, the first prototype of the Apus i-2.
The door opens, we walk through, and there it is.
There it is, fully assembled now with all structural components and electronic systems. At the moment, the propeller crate is in front of the airplane, which is quite symbolic, but all components are installed.
And it really looks like an airplane. The nose section is open and crammed with technology.
We see a 2-part propulsion system with nearly identical systems on both sides. The fuel cell stack is the main feature here, consisting of a stack of bipolar plates that look like a stack of cylinder head gaskets about 0.5 meter tall. This is where hydrogen is turned into electricity. On one side of each bipolar plate is air, oxygen, and on the other side is hydrogen. They are controlled and react to produce water and electricity.
And the electricity goes somewhere?
Exactly. The orange cables you see are high voltage lines. The fuel cells provide 400 volts, which are then adjusted to the operating voltage. The cables run through the fuselage to the wings and into 2 nacelles, where further converters also act as motor controllers.
To describe it, the fuel cell is about 0.5 meter tall and about the width of a hand. The cables coming out of it are about as thick as 1.5 thumbs and carry the energy. But if I look at the actual motor, it's tiny.
Yes, it's like a washing machine motor, and a bit bigger of course, but similar to a car motor. This motor can deliver up to 150 kilowatts, but during cruising flight it uses around 100 kilowatts, just enough to match what the fuel cell provides. And that's what powers the aircraft.
In the following minutes, I speak with Enrico Plans from Apus. He describes how he removes a flange from the Iron Bird to attach the propeller to the i-2 and explains why screws with marks on them are crucial for the plane's safety. For authenticity, this part of the podcast is not translated. Afterward, the English version resumes.
So, jetzt stehen wir also hier vor dem entstehenden Flugzeug und vor dem Flugzeug liegt eine riesige Kiste. Und was da drin ist, da spreche ich mit
Enrico Plans, hallo. Und zwar liegt dort der Propeller drin, der letztlich, also einer von 2, der letztlich das Flugzeug antreiben wird und in die Luft heben wird. Und da bin ich gerade dabei, die Flansche, die Adapter, die an dem Motor dran sind, zu montieren.
Das heißt also, die Stelle vorzubereiten, in dem mechanisch Motor und Propeller festgemacht werden.
Genau, die beiden Teile werden miteinander, die einzelnen Bauteile werden miteinander verbunden, um letztlich dann das Flugzeug sicher bewegen zu können.
Ja. Und jetzt passiert was? Also du hast jetzt schon eine Ratsche in der Hand, also was passiert jetzt?
Genau, ich löse die Schrauben von dem einen Propellerflansch, den wir schon mal probehalber verbaut hatten, und werde es dann an dem Elektromotor miteinander verbinden.
Ja, und das machen wir jetzt, würde ich sagen. Gehen wir einfach mal los. Wir gehen an den Iron Bird, richtig? Genau. Ja, jetzt gehen wir zum Ironbird und jetzt passiert genau das, was wir vorhin beschrieben haben. Am Ironbird wird was abgeschraubt. Los geht's. Also der Flansch ist ein Metallstück. Genau, und hier sind 2, 4, 6, 7 dicke Bolzen drin, die es letztendlich dann festhalten.
Genau.
Da sollte sich ja nichts lösen, ne?
Das wäre gut, wenn da nichts passiert.
Da sind überall so Striche drauf. Was sagen denn diese Striche?
Genau, die Striche sind für uns eine Kontrolle, die einfach sicherstellen, um später nach einer gewissen Anzahl an Betriebsstunden feststellen zu können, ob sich die Schrauben doch gelöst haben. Wenn ja, warum? Einfach zur Kontrolle.
Jetzt werden also diese Schrauben hier abgeschraubt und dann wird dieses unscheinbare Stück Metall genommen und an den Apus i-2 gebaut.
Genau, so wird es jetzt gemacht bei uns. Genau.
To me, as someone familiar with airplanes only from looking at them, where one would expect a large complex piston engine, there is relatively little technology. The main components are here at the front and middle.
Exactly. The large equipment is for energy conversion, turning hydrogen into electricity. That's the big part. In comparison, converting that electricity into thrust is relatively simple. The electric motor is small and light, but the fuel cell systems around it are significantly heavier.
Can we see the tank somewhere, or is it hidden?
No, you can't see it anymore. It's completely built into the wing. You can see a few lines sticking out. For example, here's a small pin, which is a vent in case hydrogen leaks out where it shouldn't. It can safely be released into the atmosphere from there, but the tanks themselves are now enclosed in the wing structure and they're not accessible anymore.
So, how do you refuel?
You go to the outer end of the wing, there are various openings where the refueling valves are located, and that's where you refuel.
Hydrogen is a very volatile, thin substance. It's probably pumped in under high pressure, right?
Yes, the tanks have a working pressure of 350 bar. We even had to build our own refueling station for it, as it's not something you can just buy off the shelf. It's set up here in the hall.
So the hydrogen station is specifically for the Apus i-2?
Exactly, it's used only for this purpose, drawing hydrogen from bottles and transferring it into the wing tanks.
Now, the plane has a cockpit, though the seats aren't in yet. I assume they'll be added last. There are still a few cables not connected, but overall it looks pretty finished.
Yes, that's correct. Everything will be fully operational in 2 weeks. Some of the larger components are intentionally still missing. For example, the batteries aren't installed yet. They are currently outside the hall. But all the cooling systems are connected and sealed, and the propulsion components are all in place.
So now I suppose we just wait for it to begin.
Exactly. Once everything is fully assembled, the testing phase begins. The propulsion systems will be gradually brought online, and the software will undergo further testing. After that, the airplane will be integrated into the testing as well. We'll start taxiing here at our airfield, gradually increasing the speed until the plane nearly takes off. Once we reach that point, we'll be ready for the first flight.
Well, good luck with everything that comes next. I hope the rollout goes well, and I'd suggest we meet again when the taxiing trials start.
Ideally, you'll join us for the rollout. That would be wonderful. Otherwise, we'll see each other when the tests begin.
Perfect. Thank you very much.
Thank you too.
And just one final thing. Unfortunately, I wasn't able to attend the rollout on September 6th. During the recording of this podcast, Phillip Scheffel hinted at something special for the event. So, a few days later, I asked him to describe how the rollout was designed and celebrated.
Yes, the rollout event was a very significant milestone in the Apus i-2 project, marking our progress toward the first flight. It's the point where all the major work packages are complete and the team has achieved 95% of the project's work. From now on, the focus is primarily on testing to bring the systems online, and in about 3 months we'll be ready for the first flight. Because it was such a team effort and so many work packages were completed, we celebrated the rollout as a team event. The aircraft was pulled out of the hangar by 70 employees, each holding a rope. The plane emerged slowly through smoke and blue light, accompanied by monumental music from Back to the Future in front of 300 spectators. It was a very emotional moment. for all of us.
If you would like to see pictures of this event, you can do so on Apus' social media channels, for example on LinkedIn or Instagram. This was Mancherorts, episode 20, about the creation of the Apus i-2. Thank you for your time and patience during this recording. You can find this and other episodes of Mancherorts online at mancherorts.de or in your podcast app under the keyword Mancherorts. We'd love it if you followed us.
Mancherorts, es fliegt. Ein Podcast von Rainer Suko. Hören Sie Mancherorts. Überall, wo es Podcast gibt. Und bei Radio SKW.